Assalamu alaikum. I am Aisha. This video presents my research work during masters. It mainly targets two fields, network security and machine learning. The aim is to generate adversarial attacks on intrusion detection systems. To understand this statement, let's first have some background knowledge. So, what are intrusion detection systems? They are network security tool and essential part of today's security systems. They consist of hardware and software devices that detect malicious activity in a network. IDS can be placed on network premises or inside an host. Our focus is network-based IDS which monitor traffic passed on the whole network. Next, IDS can be classified based on detection techniques such as signature matching and anomaly detection. Signature-based techniques have certain limitations like they are unable to detect zero-day attacks and require continuous upgrade of signature database. In anomaly-based detection, IDS makes a model of normal system behavior, and the difference between observed traffic and normal traffic profile is treated as anomaly. This working of ADS makes it possible to detect zero-day attacks. That is the reason behind the popularity of such detectors. For this work, we are interested in modern detection techniques that use machine learning or deep learning. So, machine learning based ideas have been proved very effective, but a downside of using machine learning techniques for this purpose is the possibility of adversaries that try to circumvent the detectors by exploiting the implementation flaws of ML models. The field that studies the vulnerabilities of machine learning models and uses them for malicious purposes is called adversarial machine learning. For example, in this image, an adversarial input that may be some random noise is overlaid on a typical image can cause a classifier to misclassify panda as a gibbon. There are three aspects of an adversarial attack, which are attack timing, attacker's goal, and information available to the attacker. Based on the information, attack can be white box, where model and its parameter are fully known to the adversary, whereas in black box setting, the attacker has limited or no information about these. However, he may obtain some of the information indirectly, for example, through queries. There can be different reasons behind an attack, such as evading detection or reducing confidence in the algorithm. The attacker's goal behind targeted attack is to misclassify the specific input data. For example, to classify the attack traffic as benign. On the other hand, by reliability attack, the attacker wants to degrade the model performance by maximizing the prediction error. Next, the adversary can attack the model during different stages of a typical machine learning process, which results in extraction, inference, poisoning, and evasion attacks. In poisoning attack, the attacker injects corrupt or wrong data into the machine learning model's training pool, which makes the model learn wrong data distribution and hence it results in incorrect predictions. For example, in label flipping attacks, the attacker gains access to the training dataset and flips the label. Machine learning models may be trained on datasets that contain sensitive information. The aim of inference attack is to reveal that data through model probing with different inputs. These attacks destroy the confidentiality of training data and pose as security threats for individuals and systems. To launch an evasion attacks, the attacker creates adversarial examples. So, adversarial example is the carefully crafted input data with small changes that look identical to original data. This data is then fed to a machine learning model which wrongly classifies it. In extraction attack, the attacker creates a replica of a remotely deployed ML model. He feeds the target model with input data and observes the output. He sends as many requests to the remote model as possible and extract information to make a substitute model. This attack is also known as a model theft attack. So, the major difference between poisoning and evasion attacks is the attack timing. A poisoning attack is launched during the training phase, while the evasion attack is launched during the inference time or test time. As we saw that new ideas are being designed using machine learning techniques, The emergence of adversarial machine learning has posed a threat to the performance of these systems. So, there is a need to study the devastating effect of adversarial ML. So far, a limited number of research is published where adversarial attacks have been evaluated within the ideas domain. Most of the work is done in the area of image recognition. Also, most work generated attacks on outdated dataset, but new cyber attacks are emerging very quickly and current traffic scenarios have also changed. So, attacks should be performed on latest traffic dataset. Attacks on machine learning based ideas should be designed differently from typical adversarial attacks. So, a proper threat model should be developed which considers real world constraints. This section presents the most valuable work done in this field. The details of each paper are shown here. After having a comprehensive literature review and finding the research gap, our objectives for this work are shown here. The first objective of this work is to search for a good dataset. A dataset is considered good for the training of ideas if it meets certain requirements like it is released recently, it records data of real network traffic and not simulated environment. It includes a wide range of cyber attacks. The table here shows the benchmark datasets. Now let's discuss the algorithm we used for generic ideas. There are a lot of machine learning models used for intrusion detection. We tested few of them like knife Bayes, SVM, decision tree, and random forest. Random forest outperformed the others. The reason is that random forest uses an ensemble of decision trees where individual trees make their predictions while the final decision is based on majority voting, which makes this algorithm more efficient as compared to others. Next threat model was developed by considering the feasibility of different attack conditions. For example, some research work assumed that the adversary has complete knowledge of the target system and he can send unlimited queries without getting noticed. That is not the case with real-time ideas. So the fact is that attacker has no access to training dataset as well as model. He can only access the model output by sending a limited number of queries. This threat model suggests that the attack should be black box, query efficient, and targeted, where the adversary's goal is to evade detection. Here is a detailed comparison of adversarial attacks. We found these attacks from literature, and most of these are published in IEEE Symposium on Security and Privacy. These attacks have certain advantages and disadvantages, and none of these attacks match our suggested threat model except the last attack, which is hop skip jump attack. It is black box, query efficient, and targeted. While the only disadvantage is that it is highly computationally expensive. Next, our base paper implements a deep framework to perform adversarial attacks. This framework is robust to adversarial attacks, but the authors evaluated only two types of adversarial attacks. Those were optimization based attacks and distance based attacks. They mentioned in the future work section that the other attacks, such as poisoning attacks or evasion attacks, might fail this framework. In this work, we aim to test the robustness of this framework against these attacks and degrade its detection performance. Before heading towards the results section, let's discuss some metrics to evaluate the performance of our system. The first one is accuracy. Accuracy measures the number of times the model has correctly predicted the output. Even though accuracy is a widely used metric, it is universally inappropriate for imbalanced datasets. The reason is that a high accuracy is achievable by a no-skill model that only predicts the majority class. For imbalanced dataset, accuracy score is dominated by the prediction of majority class, and it is not able to capture the performance on minority class in true sense. To tackle these issues, there are other performance metrics, for example, precision, recall, F1 score, etc. Precision tells us how good the model is predicting a specific category. It is also called sensitivity. Since network intrusion is a rare event, that's why the datasets we have used are embellished, as it can be seen by class distribution on right side. There is more data of normal traffic than attacks, so we choose precision as a metric to evaluate the system. There are some of the tools and libraries we have used. Scikit-learn, PyTorch, and TensorFlow were used for machine learning and deep learning part, while ART, that is Adversarial Robust Toolbox, was used for adversarial attacks. Machine learning based intrusion detection starts with raw data. This data is then processed and useful features are extracted, such as average packet flow, throughput, transport layer protocol, etc. The next step in the pipeline is to train the model on the processed data. The trained model learns characteristics of malicious data and generalizes it on new unseen data. We trained our ideas on UNSWNB15 dataset. Size of this dataset is 100 GB and it includes 49 features. Some features in this dataset are categorical, such as protocol, service, state, and attack category. So we applied label encoding to those features in which each category is mapped to a number. Also, scaling was done to bring the features on a common scale such that each feature has zero mean and unit variance. Then the model is random forest and attack is hop skip jump. These results show that before attack, IDS has detected the normal traffic and attacks with 100% accuracy. There are no false alarms and false negatives, but after attack, detection accuracy is reduced such that it cannot detect even normal traffic. The IDS is misclassifying normal and malicious traffic. It is confusing to make predictions of both classes. Here, the hop skip jump attack has successfully targeted the reliability of IDS. Deep 8 framework used a CIC IDS 2017 dataset. The parameters for the LSTM model are shown here. These are the results from the actual implementation of Deep 8. The model designed by the authors is performing very well for attacks and normal traffic. And this confusion matrix shows that model has classified 145 normal instances as an attack, which are false alarms basically, and only 4 attack events are misclassified as normal. The precision score for both classes is more than 99%. So, to defeat these ideas, we should craft such traffic instances that fool the model and it classifies attacks as normal traffic. As a result, the attack precision will reduce for attack class while it should remain the same for benign traffic. That is, normal traffic should still be classified as normal. First attack we tested was FGSM. The confusion metric after this attack shows that only one attack instant is detected while others are predicted as normal. The precision score for the attack class has reduced from 99% to 20%, and for normal traffic it has changed from 99% to 97%, which is obvious as false alarm of the detector have increased. And second attack was hop skip jump attack. It resulted in 33% accuracy for the attack class and normal traffic was detected with 100% accuracy. Here is a comparison of attacks we tested on DPAD. The target was to minimize the attack precision, while the precision for normal traffic should be maximum. Another aspect that need to be considered is the time taken to execute the attack. As we saw earlier, that hop skip jump attack perfectly matches the threat model, but it is computationally expensive. In comparison, the FGSM attack is quite fast and does not require much computational power, but in practice the attacker should execute the attack before the incident response cycle is initiated. So we select FGSM attack to attack the DPAD. So in this work we explored the possibilities of performing adversarial attacks on existing IDS. An exhaustive research was done to select the benchmark datasets that capture modern traffic and a wide variety of attacks in real scenarios. Then we designed a random forest based IDS that was trained on selected dataset. This research proved that deep aid is not robust to evasion attacks. To defeat the deep aid detector, two attacks, hop, skip, jump, and fast gradient sign methods were tested. Both were able to trick the detector into making wrong predictions. But considering the computational cost, FGSM outperformed the hop, skip, jump attack. This work can be explored further in many directions. For example, as it was stated earlier that hop skip jump attack perfectly matches the realistic threat model, but it is computationally expensive. So the implementation of this attack should be optimized to cost less computational resources. After defeating the state-of-the-art deep pay detector, there is a need to design a defense mechanism so the attacks implemented in this work can be detected. In short, the robustness of deep 8 can be improved further.